Welcome back to the AI for 2021 Finance Summit, presented by Dot Data. I hope you're having an awesome time so far. Next up, we have two speakers from TigerGraph. We have Abhi Mehta, who's the Director of Field Engineering, and David Ronald, Director of Product Marketing. Please join me in welcoming them both to our virtual stage.
Hello and welcome to our presentation called Transforming Financial Services with Machine Learning and Graph Databases. Gartner, one of the most widely respected market research firms, has said this about graph. Graph analysis is possibly the single most effective competitive differentiator for organizations pursuing data-driven operations and decisions after the design of data capture. Gartner is a huge proponent in the value of graph. The company has published a number of reports on graph analytics. And one of these, called Understanding When Graph Technologies Are Best for Your Business Use Case by Jim Hare and others, describes the 6 types of graph analytics. Let's go around that hexagon, starting at the upper left. Path. How do we find optimal paths or evaluate route availability? Community. Where are the clusters? What are the areas of focus? Centricity. What are the most important points in the network, either inside a community or outside of it? Similarity. How similar are nodes or groups of nodes in the network? Link prediction. This is all about determining the likelihood of nodes forming or breaking connections. Last but not least, connectivity. How strong are the connections between nodes? You tie all this together, and it's not much of a leap to say that this is how we can transform financial services and fight financial crime. Because we can find paths, we can uncover communities, we can identify centricity, we can measure similarity, we can predict links, and we can measure connectivity. Here is a simple representation of what a graph database looks like. The circles are the vertices, and the lines are the edges joining the vertices. Vertices are data concepts. That could be something like a person, an account, a transaction. And then the edges are the relationships between them. For example, a person opened this bank account, or money was transferred from this account to another account, or money was transferred from one account to a realty. And a graph stores the relationships between data entities, or can be used to uncover the relationships between those data entities. And that's one of the key differences between a relational database and a graph database. The former, a relational database, puts data into rows and columns in tables, and joins are required to move from one table to another, whereas a graph has those relationships stored inherently and doesn't require multiple joins. And I'd like to just share this overview of how customers are benefiting from graph databases. At the upper left there, one of the benefits of a graph database is connecting data sets and pipelines. United Health Group, for example, is using us to improve the quality of care they provide to patients by connecting over 200 data sets and pipelines and bringing that information into a central graph. A Fortune 50 retailer is making personalized and relevant product recommendations on its e-commerce site by connecting together over 100 different sets of data. Xandr, considered by some to be the gold standard in advertising and advertising analytics, is using us to build an identity graph from over 50 different pipelines. At the upper right, we can analyze connected data. Jaguar Land Rover, for example, is using us to accelerate supply chain planning from 3 weeks to 45 minutes. 3 weeks to 45 minutes. China Mobile is using us to scan over 300 million calls a day and detect and block fraudsters. And then finally, at the lower right, you can learn from the connected data Intuit, which is a company in the financial industry, financial services space, is using us for AI-based customer 360, entity resolution, and fault detection. So the summary here is that we have a unified platform that performs 3 roles. It's a distributed graph, it provides advanced analytics, and it supports amplified machine learning. And with that, I will pass things over to Abby.
Thank you, David. Let me share my screen very quickly. All right, wonderful. Thank you, David, for giving us the updates and a head start over here. So, ladies and gentlemen, let's look into the use case where, a real world financial use case. We are going into the logical view of this use case. We will look into the semantics of this use case. So, this is something you may have performed this morning itself. As a customer and account holder of whether we have a credit card, we may have done a transaction, right? And when you do a transaction, we have used a particular kind of device. So a device utilized once, the bank knows that this device is related to some particular account. And of course, as we know, it takes 2 to do a transaction. So there has to be another account on the right-hand side. And this account belongs to somebody else that has all the details the same way the account on the left-hand side do. So what we are trying to get at over here is that this is a logical view. When you lay out your use case on a chart or a piece of paper or on a diagram, this is what it looks like. It's so simple. But finding the correlation between your data set, for example, how is a customer 1 and customer 101 related? It's a very easy in this logical view. All you need to do is go to the next element, which might be a table, which might be a linkage, and just say, okay, this is the pathway we follow to get to the information we need. But that really isn't the problem. This is not really the challenge. This is actually a much bigger challenge when you look at the technology behind the scene, which you and me, most of us are actually used to. And that is RDBMS. It's a 2-dimensional structure behind the scene. It may look like something what you're seeing on the screen, right? There may be transaction, user devices, user tables separately. There might be device tokens in between. And if you are looking to find out correlation between 2 user sets, if you say, oh, Abhi transfer money to David, David to Mr. A to Mr. B, and Mr. B did transfer money back to to Abhi, all you need to do, it's easier said than done. You have to go into these tables and you are going to make the Cartesian joins in between them. And depending on what depth you want to go, this is basically cost prohibitive. The compute power, because of the RDBMS joining problem, is so much that it becomes cost prohibitive to find and expose the hidden patterns inside your data set. So this ad hoc query firing, the random extraction of information from your data set using 2-dimensional structure is virtually impossible and cost prohibitive at least. So if you look at the graph, which I was showed you earlier, and if you store your data inside a graph structure, this is exactly how you're going to lay, this is exactly how your layout of the land would look like. Each node, just based on the edges between them, right? Between the linkages between them, as David was explaining earlier, knows what it connects to. So it's a kind of adjacency matrix. It's basically exactly like a navigating the path from one point to another to its nearest first hop neighbor and finding the path forward. That is exactly why the graph technology is so different from the existing 2-dimensional structures of either RDBMS, or you look into the NoSQL stores. So let me demonstrate this capability to you first before I go into the use cases where we will explain to you how top 7 banks in the world are using graph for various different kind of strategy on the fraud detection side, machine learning side. So let us get very quickly into a demonstration. I will not spend too much of time. Our products have hundreds of capabilities, so don't make up your mind in case you want to see some coloring mechanism, or you want to see some shell scripting, or you want to see capability of any kind of RESTful APIs. Our system actually provides you all of that. But over here, as I was showing you, a use case is much more simpler. And what you're seeing here is a user doing transaction, takes 2 to do a transaction. They're using a device token. Device token could be something as simple as a PDA, and payment instrument could be a PayPal account or your credit card information. So this is a very basic use case. As you can see, various different attributes, just like you would have on your RDBMS. And the data is already preloaded into my system. You can see billions of records. You have a billion vertices, 4 billion edges, 880 million payment instruments. So it's a sizable chunk of data which has been loaded inside the system. And now we are going to show you how this is totally different from RDBMS technology. Let me show you quickly. Let me pick up a couple of users, like just 5 users on the top, and I'm going to drill down into one of them. As we double click on it, as I was saying, one hop away, this user know where it can navigate to. All the transactions of this user, all the devices they have used, device tokens, and all the payment the instrument this user has ever used is right here visible on your screen. Now, visibility, the visualization is only one aspect of graph solution, right? I mean, that is just a byproduct of the engine and the schema what you have created behind the scene. Let's look at this particular transaction. It takes 2 to do a transaction, so there has to be another user, and this user lives in his own world. If I double click on it, you would see tons of information. And of course, every transaction this user number 4615 does will also have another user on the right-hand side. So the idea here is not just to show you the visualization and the schema capability, but to focus on a point that when you store the database in data in your RDBMS system, you're basically storing in rows and columns, right? And if you are hopping from one kind of data to another kind of data or looping through it, you're creating the joins, and these joins are extremely inefficient. But on the graph side, you don't make any such joins. You're basically hopping from one memory space to another. And what does that mean? That means that if you are finding correlation between 2 different kind of data sets, it's very, very simple. All you need to do, tell the system, go ahead, expose the hidden pattern inside this data set. And here the system goes over billions of records, came back in a matter of milliseconds, telling you that this user did a transaction with another user who did a transaction with this user that was referred. It's as simple as that. Finding and traversing the path inside the graph databases. And on top of TigerGraph, which is a distributed graph, it's much more simpler task. But most of us, that's not what we want. We are looking for something more. We are doing fraud detection scenario, anti-money laundering scenario, maybe portfolio management or wealth management use cases that require some specific business cases. Let me show you one of that business case programmed in G-SQL programming language, which is very much like SQL. It's a custom business logic. What it is doing a network analysis of when a transaction comes in, the system finds out that it takes 2 to do a transaction logically. So there are 2 users, and these users have their own network of devices that they have utilized in the past. And those devices may have been used by other people. It may be, some members of his family using it, or maybe it's a merchant whose credit card machine has been used by many different users too, or customers too. So there is a network of the users on the left and right hand side of transaction. And what we're trying to find out here with this query over billions of records in sub-second time is that all these guys up to 4 hop down, are they transferring money into each other's bank account? So here we go. And the results are already back. Over billions of records, no caching involved. And here we go. You see the network on the right-hand side of this user and all the device-based transactions coming from the middle here. On the left-hand side, the other transaction doer and his network of devices. And as you can see, right in the middle, there is a transaction. Amount is just $7, but they have been crossing over and transferring money into each other's account. Imagine this as a circle detection, a query for your machine learning algorithm to do mule network detection or network analysis of your data set, or maybe using it for investigative purposes. So that graph databases make it possible for you on real time to do these kind of analysis on a huge set of data. And that is the biggest value which TigerGraph provides you. And of course, there is much more to it, right? I mean, any business logic is limited by your and my own imagination. What is that we want to do? Means here is another example of finding how much money one user's network has been transferring into each other based on a particular time zone, right? The time series data comes into picture over here. Again, sub-second query response time. This time we are not interested in visualization. We just want to look at the JSON file. And you see over here, now you can integrate with your any application framework using this JSON REST API integration. And system went ahead, navigated the path, found the correlation, and calculated and summed up all the transaction on certain dates. So all what we are trying to get at with giving you this example and demonstration is that using graph databases, you can do things which you would have never thought of doing earlier inside fraud detection system. You know, T+1, T+2 systems can be turned into real time on a terabytes of data set. Very quickly, a little bit of chest thumping. And thanks, David, for starting that up for me. Let me add to it. The top 7 banks in the world are using TigerGraph for various different kind of use cases. You may be able to find, correlate with some of these use cases over here: credit card scoring, wealth management, trade surveillance. And again, let's take an example of anti-money laundering system. If you are related to those kind of use cases, if you had a traditional AML system with a narrow and a static viewpoint of transaction, you may not be able to do this flexible rule set what I just showed you, right? Doing all these transactions on billions of records in real time. How would you detect fraud rings? That's where you need a lot of analysts doing manual operation. What if you get a new list of politically exposed people or global watch list, and now you want to run it against all the data you have from last 3 months? How would you do that? Very expensive, overnight process, not real time. So here is an example of one of our customer who has used us for anti-money laundering scenario, use case, which they have created on TigerGraph, and they wanted to improve accuracy. 80 to 90% of false positives these guys were getting, right? This bank was getting 80 to 90% of false alarms and alerts coming out of their system with the traditional AML solutions, and they wanted to improve that. And of course, they wanted to uncover the non-obvious relationship, just like I was showing you on the previous example, that maybe this device is used by X and that device is used by Y, and one of them is compromised. So there is a low confidence that the first device who's participating may also be compromised, may also have been compromised. So using our system, they are able to bring in 10%, increasing the accuracy of finding the frauds by 10%. And definitely $2 to $4 million they have avoided using avoiding the fines from the regulators because the accuracy was going up. Of course, we are not showing you the numbers over here for the false positive reduction, but what we concluded, it's something like a $20 million they have saved on various kind of hardware to software to people resources using TigerGraph technology. Building on the same kind of example that I was telling you earlier, when I was showing you a circle detection in a use case, this is also pivotal to your machine learning and AI strategies. Let's look at this example over here. Training data set, if you need to do these kind of smart feature extraction, may have to run overnight. Testing data set may also have to go through a lot of challenges to get these kind of fine-grained features out of your traditional two-dimensional structure. Doesn't matter even if you use Spark, if you want to make it real time, how are you going to manage it? But when the customer started using TigerGraph for feature extraction, not just for our algorithm, just for feature extraction, they were able to drive way more transactional analytics on their data set. So example being total number of fraud detected for a merchant. Why are you interested? Okay, maybe this is a good factor to go into your machine learning algorithm. Is there a circle in this transaction? Is there more than $20, more than $50 of transaction happening between two network of people? So doesn't matter what kind of features you want to extract, technologies like TigerGraph, especially backed by the graph technology that we have, is going to benefit you in a very big way. People have just totally transformed their accuracy levels using graph technology. And here is another example of mule network. This is more like a Frankenstein fraud on the credit card data, credit card loan data, application data. If somebody has been trying to register from a device which has been compromised or been marked in historical context as a fraudulent, can we give a low confidence to the new loan application which is coming in, or new credit card application which is coming in? So 20 terabytes of data over here. Within 6 weeks, they were able to prove the concept out, and 3 months to take it into the production. That is the speed at which our teams operated and worked with them, because we have a lot of knowledge, historical knowledge, and of course, the consulting knowledge by working with various different financial institutions for the newer algorithms which are used in fraud detection these days. And the next example is exactly coming out of that experience that we have gained at another top US bank. So this is a combination of graph algorithms, page ranking, and Louvain. Now, when you store your data in a graph format, you not only enable the easy traversal and summations and calculation and exposing the hidden patterns, you also enable newer kind of algorithms which can run on this graph-based structure. And this provide you more machine learning capabilities and possibilities. Example being page ranking and Louvain. Let's say I have a CVS in my neighborhood and a Rite Aid. A lot of people go to both of the stores. So can you combine those stores, saying that based on the density of the people living in a certain community going into those directions, maybe these stores are interconnected with each other. And if the stores are interconnected, just like Google ranks your search results, bringing the top results on the top, can you bring up high value merchants in a certain zip code or locality? Right? That's the page ranking algorithm you can apply on the graph-based structures. Now, if this is what you can do, you can also do community detection based on the material they sell, the kind of quality of stuff they sell, from cigarettes to diapers or whatever you want to do, right? And you detect those tiny communities of the merchants based on the various different attributes which can go into the community detection. And with page ranking and this community detection together, now you know what are the highest value customer in a certain zip code. And if you have some fraudulent transaction or fraudulent card holders or fraudulent merchants in those kind of areas, in those kind of communities, now you know what communities have been damaged the most by your fraud rings or fraud activities by the merchants or the credit card holders. This is a very interesting use case. Will take more than few minutes for me to explain, but this was another huge value on a 10 terabyte of data set. Which we were able to bring to our customer. KYC, know your customer, based on the FIBO ontology, right? Financial industry business ontology. If you are into knowledge graphs, that can also be mapped inside TigerGraph. And you can use property graph like TigerGraph for deep analytics. So that's also a possibility. That's where our customer also lie in the financial domain. They are more on the hedge fund side. The reason why TigerGraph can do this and we perform better than some of our competition is because ground up, we are a distributed graph database. Earlier, there was a scale up systems in the graph world, and that's why they were not getting too much of popularity in the large scale data sets. But now we have resolved that problem by creating a distributed graph. Being distributed graph, you can scale it out on a cheaper machine. You can have better core utilization. You can parallelize your graph algorithms so that the work which was earlier taking a day now can be done in hours. And of course, TigerGraph also have a multi-graph capabilities which take care of regulations and compliances. The product department shouldn't see the data from customer department, and the customer department shouldn't see it from product department. Maybe they can't see each other's password, or maybe they share some credit card information. So you can bring logical segregation of your data over your data set using our multi-graph services. It's an asset compliant database, OLTP, transaction processing, and analytic processing. So that's also part of our system. And we compress your data down up to 40 to 60%. So you use much lesser on the hardware side and on the machine side. So this is all together forming the basis of your futuristic development on graph databases. So I would, for any detailed conversation, I will welcome you to join us on TigerGraph Cloud. Reach out to us. You will have our email addresses just flashed out. And all what I have shown you right now is also available as a starter kit on our TG Cloud instances, which are given out free at this time. You can go in, create your account, and verify what I just told you today. With that, I will be, thank you for joining us, and over to you back. Thank you.
Awesome. Thank you so much. Thank you for sharing these awesome insights with us. We really appreciate seeing how this incredible product works. All right, for the audience, it's time for you to go ahead and make your way to your next session. But along the way, make sure to check your connection requests and accept those, as well as checking out our AI exhibits. Thanks so much, and we'll see you around.